I've struggled over time to try and figure out what it is about the topic that people get or don't get. And it's a challenge because I first encountered it with my son when we were dealing with physics. My son is getting a PhD in psychology, and he's done biochemistry, and he's done a variety of things. And this is one of those topics he didn't necessarily get. And it's kind of like, okay, why? So I'm going to give you a heads up right now that this is a topic that I don't understand why you guys don't get it. And this is one that I can usually give you 20 different reasons or 20 different explanations for a variety of different topics. This one, I just don't get why you don't get it. All right? So I'm going to tell you that right up front. I may sound frustrated at times, and it's because I'm frustrated with myself, not frustrated with you guys, because I understand that there's an issue there. But it's a frustration on me that I can't figure out a way to help you guys understand it, because to me it's like, it's so simple. It's so simple. So let's talk about where we are. Now, we've talked about early on, if we look at Newton's second law, and we've even talked about that ahead of time, and when we talked about Newton's second law, I indicated that there's a couple of ways to look at it. And so the way we've looked at Newton's second law so far has been that the summation of forces is mass times acceleration. This is a vector quantity, and that's a vector quantity. We also talked about that we have that our force is equal to gravitational constant, mass 1, mass 2 divided by r squared. And we even went through this to show that if we looked at the mass of an object, that this g, mass of the Earth, over r squared, that this worked out to be our field force due to gravity. So we actually got that part to where we had looked at it. So we have an interesting piece associated with it. So that still is a form of Newton's second law, because we went through that was gravity. But I also talked about the fact that when Newton actually looked at this, when he actually said, all right, this is the second law, that's not what he said. He said, because we talked about this inertia, this property of inertia. And what we looked at in inertia was, if I have something big, large mass, and I have to apply a force to get this mass to go into motion, that the force that I had to apply was going to be proportional to the mass that I was doing. So the force in order to get this to move versus the force in order to get a little mass to move was different. And the force was going to be proportional to the mass. We're going to have to, in order to get this thing in motion, I'm going to have to apply a bigger force than in order to get this small thing in motion, I'm going to have to apply a different force. And so that force was proportional to mass. And that related to inertia. Now, from a fundamental point of view, and from a prospect that we all know, okay, so I'm going to be in my little truck. Remember, my artistic abilities are limited. So I've got a truck here. And we're going to approach a stop sign in the truck. Get my little stop sign on my truck here. And if I have a person in the car, and we've all watched Crash Test Dummies, right? I've got my person in the car here, and I hit the brakes, and if I don't have a seatbelt on, what am I doing in the car? If I hit the brakes, what happens when I'm in the car? I'm going to continue to go forward. Because Newton also said an object in motion remains in motion unless acted upon by another force. Right? So we've got an object in motion remains in motion unless acted upon by another force. So unless I have my seatbelt on, we're going to continue to slide forward. We'll actually continue to slide forward, and we have that prospect there. So if I'm sitting here, and I'm going to use my hockey puck analogy, my hockey puck is going to continue to move forward. So we've got those two things that are working towards us. So basically, what Newton was saying is we have this inertia, and my force that's being applied in order to get this to move, I can apply that over a piece of time. Okay, I can apply that over a piece of time, and that's going to equal what we call a change in momentum. Okay, a change in momentum. And this becomes momentum. And we actually talked about this a little while ago, that this right here is an impulse, and we end up with a change in momentum. So if we look at it from a hockey puck point of view, if my hockey puck is sitting on the ice, it's not going anywhere unless I strike it with the hockey stick, and then it's going to take off and go out there until it hits the boards, and then when it hits the boards, it's going to ricochet off. And we know a lot about how that ricochet works because we've played with it, and we've played with it in the past. So if I have a hockey puck coming into the board, it hits the board, and it goes off in this direction. One of the things that we know is that the velocity that it comes in with, the magnitude of that velocity, ends up being the magnitude of this velocity. Now, but we did have a change in that we had a change in direction. So we had a change in direction, and therefore we end up with a change in momentum. Because I haven't told you what momentum is yet, but if you might remember, we said momentum is equal to mass times velocity. Now, I don't know why we use the letter P. I have no earthly idea why we use the letter P, but we use the letter P. And actually, the last time you probably seen, the only time you actually see me write it like this is right now, because that's how our book does it. I very rarely say, oh, by the way, P is momentum. Now, my momentum is going to be in the same direction as my velocity. So I've got my velocity and my momentum are in the same direction. My force is a vector quantity, so momentum is a vector quantity. Momentum also has weird units. It doesn't have its own units. It's actually kilograms, meters per second. So it has these weird units that we have to deal with. But we have momentum. Now this is also one of those things that somebody's going to ask, well, if you just gave me the equation, I know how I can work the problem. When we start working with momentum, I can't just give you the equation because the equation comes around based on how we actually work the problems. Because what's going to happen is we end up looking at the system from both perspectives, and I can't just say, okay, this is the equation you're always going to use, because it's not. You have to develop your equation for each case that you're working with. So let's look at this a little bit more to kind of talk how that works through. The fun part is, I think this is where we actually showed it before, right? This is where we actually kind of talked about it and showed it before. If I write this out as force times my change in time is equal to my change in momentum, and my force change in time is equal to my change in momentum, mathematically, I can actually rewrite this a little differently. I'm going to do the change in mass times the velocity plus mass times the change in velocity. Right? I'm going to divide both sides. That's my force times my change in time. I'm going to divide by the change in time. So this is my mass, change in mass divided by the change in time times velocity, plus the mass, change in velocity divided by the change in time. That's mathematically allowed, all right? So for those of you who haven't seen it, this ultimately, if you end up doing calculus and actually go into calculus and start working with calculus at the end, what you'll see is that this change in velocity with respect to change in time can also be rewritten as a derivative. And this rule comes out of being able to play with it from the calculus out there, but we don't necessarily need to do this from the calculus. But we want to look at this part of the equation. So just know that this ultimately is where calculus starts coming into play. We don't necessarily need it, but that's one of the things that we have. But let's look at this equation here. So if I have the force, and now I've got velocity times my change in mass with respect to my change in time, and I have my mass times my change in velocity with respect to my change in time. We know what this is. I think I heard it. This is equal to acceleration. So that term actually becomes my mass times my acceleration. What's interesting here is that we've got this term hanging out here. That term right there. So let's think about what's happening in reality. So we're going to look at this piece. We're going to think about that for a little bit. I'm going to see if I can get a better pen.
So change of V divided by change of V equals A.
Change in V divided, because remember back in the first chapter, change in velocity with respect to change in time was defined as acceleration. Okay? That was defined as acceleration. So what I've got now is I've got this expression right here is velocity, change in mass with respect to change in time plus mass times acceleration. Now we know, because we've been working with it and we've played with this, that this is our common form of Newton's second law. But now I've just shown you we could have it in this form. But that's not the form we usually use. But let's go to our hockey puck example. Okay? If I have a hockey puck and I've got a force that's been applied, so I have a force that's applied to the hockey puck, we know that it's going to go off mass times acceleration, right? We know it's going to go off mass times acceleration. But in this system, the question is there a change in mass with respect to time? Well, unless I'm stepping on the hockey puck and crushing it with my skate, I'm not changing mass. There is no change in mass. The change in mass is equal to 0 in that system. The change in mass is equal to 0 in that system. So I don't have to worry about the change in 0. So this expression in the hockey puck case simplifies to the one that we know and love, F equal ma. All right, so I'm going to look at my Dr. Seussian little vehicle here. And my Dr. Seussian little vehicle, even if it is a Honda Fit or a smart car or something along those lines, we're still talking something on the order of 1,000 kilograms. Okay? Talking something on the order of 1,000 kilograms. If it's 2.2 pounds per kilogram, thinking about that, so we can kind of get a rationale here. That's going to mean it's about 2,200 pounds. And if we put people and stuff in the car, let's say between the car, that's the car, and we put a person in it, and we put a full tank of gas. Okay, full tank of gas. Now, for those of you who don't know, 1 gallon of water is approximately 8.8 pounds. One of those interesting numbers that I keep in my head is maybe it's more like 8.3. Something on that order. Okay? 1 gallon of water is approximately 8 pounds. 1 gallon of gas, and this is one of those things because I worked in the oil industry for years and years and years at the refinery. I happen to know this number. 1 gallon of gas that you get at your gas station is about 6.3 pounds. Okay? Happen to know that. And on a smart car, it's probably about, if we're lucky, it's about a 12-gallon tank, right? If we're lucky, it's a 12-gallon tank. So we're going to have to do a 12-gallon tank. We're going to multiply that by 6. It's like 72 if I've done my 12 times 6 right. So 72 pounds. We're going to add a reasonably sized person at 120 pounds. So now I've got 2, 2, 0, 120, and 72 pounds. So I've got 2. I got 11. And that's 4. So we're at about 2,400 pounds for my vehicle. They're at 2,400 pounds for my vehicle. If I've got a smart car, the typical miles per gallon is about, we're gonna be even reasonable, say the person's driving kind of funky. We're going to say about 40 miles per gallon. So I'm going to use the distance between Tonkawa and Enid. Distance between Tonkawa and Enid is roughly about 70 miles. Okay? As the route goes, not as the crow flies, but as the route goes. Actually, it's a little less because you can do it in about 45 to 50 minutes between here and Tonkawa.
Shoot. You need to scoot the paper up.
Okay.
There.
So it's about 70 miles as crow fly, or as we go. So I'm going to use less. I'm going to use less than 2 gallons of gas going back and forth, or going to Enid from here. So if I did that, if we actually consume 2 gallons of gas, my initial mass is my 2,400 pounds. My final mass is going to be, if I do 2 gallons, I'm going to lose 12 pounds on that, right? So I'm going to be at 24 or 23.88. Somebody get a calculator out because I didn't bring my calculator this morning. So if I do 23.88 divided by 2,400, this is pounds and pounds, what's the value? So this ends up being 0.995. If I round it, I'm still at 1. So my change in mass is about 0 on all practicality. So even when I'm using a car example, I'm not changing my mass enough to make it make any difference. And so I can still use F is equal to MA without having to worry about that extra term. I don't have to worry about this extra term for my car, and that's using a smart car. So even if I'm using a bigger vehicle, and if I'm going on a semi-truck where I've actually got a large gas tank, but because of the load that I've got, even then I don't have to worry about it so much. So even though we actually have this real life term here, which you guys will see at the end of this chapter, because there is a case where this makes a huge, huge difference. I got a big case where that makes a huge difference. Most of the time, I don't have to worry about the math. I don't have to worry about this term, which is why we can simplify it. Most of the time, I don't have to worry about it. So let's talk about the time when I do have to worry about it. And since we were doing cartoon physics last week, we can do cartoon physics this week. We can even go with Wile E. Coyote. Or in my house, more prevalent, Marvin the Martian. I got my other fin up here, so we got it up here. Now, if I'm doing rocket science, I gotta worry about this term. Because in my rocket, the fuel consumption is such that I have a change in mass with respect to a change in time, and I gotta worry about that part. And so we end up worrying about that quite a bit when we're dealing with rockets. Because if I'm dealing with rockets, because if you guys remember looking at the space shuttle, when the space shuttle first took off, we had one fuel tank. And the space shuttle actually was riding on that fuel tank, and we had two booster tanks off of this side. And all of that was to get it to get up. And so the payload piece was this little bitty piece, and so looking at the change in mass of my whole system became very, very important. So most of the time we can go with F is equal to mass times acceleration, but some of the time we have to worry about that, and that becomes what we call our rocket science stuff. Because we actually have to take into account our change in mass. So, we end up with this part a lot. Going back to where we started today, I've got force times my change in time is equal to my change in momentum. This, we talked about the fact that it's called an impulse. And that becomes important because we can look at it for a couple of different ways. My little cleat, my little shoelaces here. Because when I kick it with a soccer ball, or kick a soccer ball, the actual force is only being applied over a very, very brief time. Once the ball leaves the foot, the ball is now traveling with a velocity, but there's no more force being applied. Once it leaves the foot, there's no more force being applied. We also know, because it's Major League Championship Series time here, I have my baseball bat. I got my baseball coming in. The ball's going to hit the baseball bat, or the baseball bat hits the ball, and I get a change of time, and the baseball comes flying off in a different direction, and it no longer has the force applied by the baseball bat. So we see this a lot, and we know if I'm dribbling the ball in soccer, my foot is in contact with the soccer ball for a lot longer period of time than when I'm giving it a swift kick. Same here, if I'm going to be a home run swinger, I'm applying my force over a very short period of time in order to get the ball to go out that way. But if I really want to get a good change in momentum and I do a bunt, my ball is in contact with the bat for a lot longer period of time. We see it in pool. You know, if I have a pool cue and I apply the pool cue there. If we put English on the ball, it also depends on where I'm going to actually apply the cue to the ball. But I can actually put a slow time, so a longer time where my delta t is longer or my delta t is shorter. So we look at that impulse and momentum. Now, over the next couple days, I'm going to post on Blackboard some videos that actually go into this quite a bit. One is a very dry British man who actually does it. He does a very, very dry piece of British that they actually go through and show the calculations. And that's a really good one to look at. But we can actually look at impulse over time. And then I've got a National Science video, National Science Foundation video with hockey that actually shows it as well. So we get that change in momentum is equal to my change in impulse. So impulse is related to momentum. And impulse and momentum allows us to do a few other lovely science tricks as well. So we actually play with that part. So we get that. So we can actually move and do a variety of things with momentum. Okay, let's see. Don't want to do that problem yet. Don't want to do that problem yet. So we actually get that part. So let's take this a little further. I'm going to switch kind of topics a little bit. So now we've got, so here's our toolkit. So we have a toolkit. And our toolkit, let's see if I get a better pen. My pens are starting to die. Because we've done velocity final is equal to velocity initial plus acceleration times time. We've done v final squared is equal to v initial squared plus 2 times a times the change in position. And we've done a change in position is equal to the velocity initial times time plus 1/2 at squared. We have the summation of forces is equal to mass times acceleration. We now have force times the change in time is equal to a change in momentum, which is equal to a change in mass times velocity. We have our force due to friction, goes like that. We've been working that kinetic energy is equal to 1/2 mv squared. We've talked about potential energy is equal to mgh. We have conservation of mass. We have conservation of energy. I'm about to add one here in just a second. So we've had this so far. Okay, we have conservation of mass, conservation of energy. We've done kinetic energy. We've done potential energy. Oh, we did work. That's force. And I'm going to go ahead and put the dot product in here for distance. So far, that's what we've done. Now we're going to start pulling some of this together, but here's the new one. And we have conservation of momentum. Conservation of momentum. And in conservation of momentum, we say that the initial momentum has got to equal the final momentum. Okay? The initial momentum's got to equal the final momentum. And so we can think about this. So let's think about it, and let's think about it from a practical standpoint. So I have a marble. And the marble has a little mass here, and it's traveling at a velocity. And we're going to hit another marble. And most of us have played marbles. And if the marble is the same mass, this is the before situation. We know what happens. So if I have a marble that comes in and I hit it with hit the other marble and everything's perfect, my first marble stops. And the second marble goes off at the same velocity that the first marble came in. And most of us have played marbles. And usually we have a steely, right? We got a steely, or we got a little bit bigger marble. And what usually happens is this one doesn't stop. It kind of dribbles off, right? It kind of dribbles off, doesn't have a whole lot of velocity. But I've transferred that velocity to the other marble. Same with pool cue. If I hit a cue ball and if I play billiards, I have the same situation that happens. And so in reality, what happens is I get that because what happens here is that the momentum before has to equal the momentum after. So the momentum, or the momenta, depending on, that the momentum stays the same. And we know this because we've played with that. We've played with it over and over again. We've played with something called Newton's cradle. You know, it's always been on somebody's desk. Somewhere around the way. You always have it on somebody's desk. Oh, let's see. I'll try the blue one. See if the blue one's any better. And if I look at it from the side, I've got this series of balls. And if I raise this one up and have it come in, we know this one ends up swinging off the end. And we played with it, right? We've played with it. We can take two and move it back. And when we do the two, these two move off to the end. You know, if we raise this one back and we move it off to the end, we've seen this, and then it comes back and it swings back and forth and it knocks back and forth. These are a series of collisions, and I will actually post a video that the guy goes through it in painful detail as to exactly what's happening. But basically what happens is if I have one ball here and I raise up another ball and I come in, I'm going to kick this one off, and I'm going to have the momentum before has to equal the momentum after. We know that the momentum before has to equal the momentum after. So we're going to start by looking at what we call, there are two types of collisions. The one that I just described with one ball and another ball, and they come in and they hit each other and they don't stick. They don't stick. We usually refer to these as elastic. And there's actually a special condition associated with it. Because in most of the time, we don't get, even though we can presume collisions like marbles, hockey pucks, billiard balls, most of the time these kinds of collisions we can actually approximate as an elastic collision, because that's how it actually kind of works out. We don't necessarily see a whole lot of loss. We get that. Or we have the kind that it happens to us a lot. So I've got a bullet that goes into the block and the bullet stays in the block. Or I've got an arrow hitting the target. Or I've got my choo-choo train hitting the little Volkswagen Beetle. These are called inelastic. I have elastic collisions and I have inelastic collisions. I've got elastic collisions and inelastic collisions. Elastic collisions have a special condition, and we'll get there as to what that special condition is. But we're right now, for the time being, we're going to assume an elastic collision just to kind of help us do some problems. And we'll look at inelastic collisions, and we'll just be playing with certain collisions. So, one of the things we talked about last Friday is I have a spring. And we got a ball. Okay? So we're going to use a spring gun here. We're going to send off a ball. So we're going to have a spring, and we're going to say that the spring constant of this spring is going to be, we'll give it 100 Newton meters. And we're going to use it as a toy gun, so as a toy spring gun. So we're going to give a change in our spring. This is going to be on the spring. So we're going to get a change on the spring, and we're going to go ahead and say that this is 5. Oh, no, we don't want to do 5. We're going to do 2 centimeters. So somebody's going to have a calculator out because I didn't bring my calculator. So we're going to have that change in meters. We're going to have the mass of my ball, and we're going to say it is 50 grams, so it's 0.5 kilograms. And we're going to shoot it at a target here. Okay? And this target is going to have a mass of, we're going to double it. We're going to have it be 100 grams. And we want to know that the velocity after the target hit. Okay? So we're going to let this go off. We're going to assume that there's nothing we're going to break off this on a fine filament. It's easily to break off. And we're going to assume that the ball is going to hit it dead on, and we want to know the velocity after the ball goes off. So I've purposely made this just a slightly bit complicated because I want to work through another conservation of energy problem. But now we're going to combine conservation of energy and conservation of mass, or of momentum. Okay? So we're going to take this system first. So we're going to look at this part. We're going to look at that part. Because in order to figure this out, I got to know some information about the ball that's going to hit it. So on this end of the problem, we got to use conservation of energy. because what I need is the velocity of the ball that is the bullet. Okay, I need the velocity of the ball that is the bullet. All right, so potential energy of the spring is 1/2 kx squared. So this is going to be 1/2 my 100 newtons per meter times my 0.02 meters squared. So whoever had their calculator out, plug that one in. Actually, just with 1. Yeah. Okay. So it's 1 joule. All right. That's a good number to help me with. I picked good numbers today. All right. So conservation of energy says that the potential energy of the spring ends up being the kinetic energy of the ball. Because I'm going to transfer the energy from the spring to the ball.
It is not 1.
No, it's 0.02. I didn't square it.
Yeah, it's 0.1 to the square. The square doesn't make
Okay, so it's 0.02.
Yeah.
Yeah, it's 0.02.
0.02. Okay. 0.02 joules.
Not bad.
It's okay. It's okay. We all punch it in the calculator. We're, I've done that before myself.
You must have just forgot a square. Oh, sorry.
So we got, but the potential energy of the spring equals the potential energy of the ball, or the kinetic energy of the ball. So I end up with 0.02 joules. So that's going to be 0.02 joules. But this is going to be 1/2 mv squared. So now I'm going to have my 0.02 joules times 2 divided by my 0.05 kilograms. That's going to give me V squared. So give me that middle number real quick. It's going to be 0.04 divided by 0.05.
0.8.
So it's going to be 0.8. Take the square root and we get, now V squared. I got to take the square root to get V.
0.894.
0.8, square root of 0.8?
Yeah. That's what I'm getting.
No.
0.894. And that should be in meters per second. So let's do the units real quick. So I've got joules are kilograms, meters squared, second squared, divided by meters. Or no, divided by kilograms, sorry. Divided by kilograms. Kilograms cancel out, I get meters squared, second squared. So I end up with, once I do the square root, I end up with that. So that's good.
Kind of weird how the bigger number.
Well, when you're on that side of the decimal place, that works that way. That's why I was double checking. So now we've got the velocity. So I'm going to go back to my picture. And this is where pictures become important. So now the velocity of the ball is 0.894 meters per second. So we used, on this side, we used conservation of energy. We used conservation of energy to get the velocity of the ball. Now, we're going to take this part of the problem and we're going to use conservation of momentum. So we're going to use conservation of momentum to deal with that side of the problem. So what we have here is that the momentum before has to equal the momentum after. Okay. So I'm going to actually write it out in words here, and then we'll put in the symbols. So I have the momentum of the ball plus the momentum of the target. And this is on the before side. This is on the after side. Has to equal the momentum of the ball plus the momentum of the target. And when you do momentum problems, you're going to find that using subscripts is really, really going to help. So what I'm going to do, I'm actually going to do different colors here to help us out. I'm going to use purple to be the ball. So this is going to be the mass of the ball. And I'm going to use the letter B for before. Because we can have a change in mass. And we'll see that, we can do it as the before. And I've got the velocity of the ball and the velocity of the ball before. Then I'm going to add the mass of the target before, the velocity of the target before. Got to equal the mass of the ball after the velocity of the ball after. And I've got the mass of the target after and the velocity of the target after. Now in this case, mass target before equals mass target after. And this one, the mass of the ball before equals the mass of the ball after. So I'm going to use this just to be mass of the ball. And I'm going to use just to be mass of the target. So that's going to simplify my equation just a little bit. So I'm going to rewrite this. So now I got mass of the ball, velocity of the ball before. And on this side, I've got the mass of the ball, velocity of the ball after. This one, I've got the mass of the target, velocity of the target before, and I have the mass of the target, velocity of the target after. So one of the things we got to look at is our picture, and we're going to make an assumption, even though the problem will probably tell you this, that when this ball hits this ball, we're going to make the assumption that it's going to be like my marbles, and this is one of those cases where we're saying it's an elastic collision, and we're going to say that when this one hits the ball, its velocity equals 0. In this case, we're going to say that, and we'll come back and we'll do it a little different in just a little bit. We'll do it a little different, and we may be able to figure that part out. But right now, we're going to use that at the collision, we're going to use that velocity 0. So now if I look at the situation, the velocity of my target when I start is 0. The velocity of my ball after is 0. Because we were told this in the problem, and we're sort of told this in the problem as well. Because we started with not a moving target, right? We started with not a moving target. Now we can have a moving target, and that can be fun too, but right now we're going to start without a moving target. So now that gives me on this side that all I have is the mass of the target, velocity of the target after. And on this side, I have the mass of the ball, the velocity of the ball before. And they have to equal each other. So I'm going to rearrange the solve for the target. So I got mass of the ball, velocity of the ball, divided by mass of the target. It's got to equal the velocity of the target after. So now we can plug in numbers. My mass of my ball was 0.05 kilograms. The velocity of the ball we calculated to be 0.894 meters per second. Divided by the mass of the target, which was 0.1 kilograms. I obviously wrote that on my picture wrong because that was meant to be kilograms. It was 100 grams. It was meant to be kilograms. So I want to get my picture right.
0.447.
And this is going to give us 0.447 meters per second. And intuitively, most of us know that if the target is twice the size, it's going to go half the speed. Because we've done this. We've played with this. We've played marbles. We've done billiard balls. So we've done this before. And so we can intuitively look at it and have those pieces. Now, most of you, I think the Tonkawa side has done the lab bit. The Enid side, I don't think you've done the lab yet. I think you do it next week. You take 2 carts. We've got our little cart. And we're going to run it into another little cart. And we measure the velocity, and then we measure the velocity after. Now, I can have a couple of situations happen when I deal with the cart. When they collide, sometimes I get a rebound. Okay, one cart goes off that direction and one cart backs off this direction. So let's look at that situation. So the mass of these carts are supposed to be approximately equal. But it doesn't always work out that way. So I'm going to use some different masses. So I'm going to take the mass of cart 1. So this is going to be cart 1. So cart 1 is going to have a mass of 0.546 kilograms. Cart 2 is going to have a mass of 0.5, we're going to make it 63 kilograms. We're going to start at the start Part 2 is going to have a velocity of 0 meters per second. Okay, we've got cart 2 is going to 0 meters per second. We're going to start cart 1 off with a mass or a velocity of, we're going to do it as 0.5 meters per second. Okay. Afterwards, we're going to measure this velocity as 0. Let's see. We're going to do 0.58 meters per second. Anybody, is that close to anything that anybody got in the lab? Or is it significantly lower? Did anybody have theirs rebound in the lab?
It was being fun because we had to do it multiple times to get it to work.
Yeah, I know one station was having a weird thing happen. Well, let's change this. Let's make this 0.47 meters per second. Now I've made these numbers up, so these aren't numbers up, so I don't know if I'm going to get a rebound or not. We'll find out.
I think I got a number like that.
Okay. So we're hitting a larger cart. We're going off at that right there. We've got this. What we want to know is the velocity of cart 1 after. Okay, we want to know the velocity of cart 1 after. So what we know is that the momentum before has to equal the momentum after. So I've got the mass of cart 1, the velocity of cart 1 before, plus the mass of cart 2, velocity of cart 2 before. It's got to equal the mass of cart 1, velocity of cart 1 after, plus the mass of cart 1 or 2, velocity of cart 2 after. That's my equation. Now, because this case we're having a stationary cart, this one we're having a stationary cart, we can get rid of that term because the velocity of cart 2 before is 0. We want to know the velocity of cart 1 after, so we're going to take that and we're going to actually rearrange this to solve for that. So now I got the velocity, or the mass of cart 1, velocity of cart 1 before, minus the mass of cart 2, velocity of cart 2 after. It's got to equal the mass of cart 1, velocity of cart 1 after. Divide both sides by the mass of cart 1. Equals velocity of cart 1 after. All right, so we're going to plug in numbers. So I'm going to have 0.546 kilograms times 0.5 meters per second minus, in this case, it's going to be 0.563 kilograms times 0.47 meters per second. All of that is divided by 0.546. Give me that one. That's kilograms. So my kilograms all cancel. So I'm in meters per second. So I'm really good. It's just a matter of doing the calculation.
Not to a negative.
It can come out to a negative.
Negative 0.21.
0.21. 0.21?
Yep.
21 meters per second. That negative is important because that says we get a rebound. And that will happen because I hit a larger current. And we know that happens. I mean, we see it all the time. That's what happens with my hockey puck, right? My hockey puck will hit the board, right? And this is very massive, right? That's very massive. And so it rebounds back in that direction. So I get a change in momentum because I get a change in direction. So we know we can have that situation occur. All right. So I'm going to do the one because I like doing it. And we're gonna look at it. We're gonna look at an inelastic collision. Okay. Now the difference, and so just so that you guys, since we won't meet on Friday because Friday's fall break, Friday's fall break, and you may want to be getting your homework done. The elastic collision is a special case. And in an elastic collision, I have momentum conserved. And this is why it's really a special case. Kinetic energy is conserved.
Was that last one an inelastic? Like the last example we just did?
This one we made the assumption it was an elastic.
Okay.
Yeah. And actually in your lab, you'll actually calculate. This one had a rebound. Usually what happens, and I'll give you the common thing that what happens with an inelastic collision, but elastic collisions have the kinetic energy is also conserved. Now I want you to note that it's kinetic energy that we're talking about because total energy is always conserved. We just may not be able to capture it all. But for an elastic collision, it's a special case. Its kinetic energy is conserved. And so we can use that 1/2 mv squared before equals 1/2 mv squared after. For the case of an elastic collision. Inelastic collisions are one where I'm going to get like combined, or I'm going to get destruction, or they're going to stick together, or most collisions are inelastic collisions. And in inelastic collisions, momentum is conserved. Total energy is conserved. But I don't have kinetic energy conserved. Okay? So inelastic collisions, momentum is conserved, total energy is conserved. Elastic collisions, I get that kinetic energy is conserved. So this, you end up with that being a special case. I can approximate elastic collisions, hockey pucks, billiard balls, marbles, those things, I can have that. But most things are inelastic collisions, and we're actually going to play with an inelastic collision. And I'm even going to be nice on my inelastic collision. So for inelastic collision, we're going to do is this one. Because we always like to do it, right? So I've got my Dr. Seussian with a cattle catcher here, okay? Got my cattle catcher, got my stack, okay? I got my train there. And everybody knows how to tell the difference between a coal-fired steam engine and a wood-fired steam engine. The fact that I have a funnel like this is because it has a spark arrestor, makes this one a wood-fired steam engine. Just a little piece of trivia. Just a little piece of trivia. That's how you could tell, if you ever see the Golden Spike picture, which one was the coal-fired engine and which one was the wood-fired engine, is one of them has a spark arrestor on it. Little piece of trivia. And we have our poor little Volkswagen sitting on the intersection. And we all know what's going to happen, right? We all know what's going to happen. It's not pretty. But we're going to make the assumption that things are going to go very, very nice, and that at the end of the collision, my Volkswagen hasn't gotten into a variety of pieces, but is muffled up on the front of my cow catcher on my steam engine. All right, we're going to use the mass of my lovely steam engine, which is not unheard of. It's something on the order, if I'm dealing with a train, it's something like 50,000 kilograms. And the mass of my lovely little car, we're going to even be nice, and we're going to say it's about 2,500 kilograms. And we're going to have this lovely thing coming in with a velocity of 27 meters per second. And remember, that's one of those interesting ones. 27 meters per second is 60 miles an hour. And we want to know the velocity of the train after. Okay? Velocity of the train after. So the momentum before has to equal the momentum after. So this case is going to be the mass of the train, velocity of the train before, plus the mass of the car, velocity of the car before. It's got to equal the mass of the train, velocity of the train after, plus the mass of the car, velocity of the car after. But in this case, the velocity of the train after is equal to the velocity of the car after, because the car is now riding on the train. We're going to be nice. Because we know what really happens, right? What really happens is the car goes off into a gazillion pieces. But it still shows you a practical part of the problem. So now I get the mass of the train, velocity of the train after, plus the mass of the car, velocity of the train after. So I get the mass of the train plus the mass of the car, velocity of the train after. This one we start out with 0 because the car is sitting on the intersection. So now I get the mass of the train, velocity of the train before equals that, and I get the mass of the train, velocity of the train before divided by the combined mass of the train plus the mass of the car is going to equal the velocity of the train after. So now I've got 50,000 kilograms times 27 meters per second divided by 52,500 kilograms. Can't be. 50 divided by 52.5 is going to be less than 1. 50,000 by 52,500. 0.95 times 27. 25.71, or approximately 26 meters per second. Train doesn't slow down a whole lot. Now, if you think about that's just the engine, it doesn't count the entire train behind it. That's why a diesel locomotive can actually hit a car and the guy not even know that he's hit it. Because he doesn't even see a change. Doesn't even see a change. So you're going to lose the train truck collision every time. The train is going to win. Every time. Alrighty. I've got that it's almost 9:20. We will see you Wednesday. No, I don't do a sign-in sheet when I'm here.